Welcome back to the course of Applied Elasticity. In this lecture, we are going to continue our discussion on different theorems of theory of elasticity. In the last lecture only, we had started our discussion on various elasticity theorems, and now in this lecture we will continue with some other theorems of elasticity. So, if you recall, in the previous lecture we had discussed about 4 different theorems of elasticity, starting from the principle of superposition, which is valid for linear infinitesimally small theory of elasticity problems, where if you are having 2 different solutions available from the same continuum under 2 different forces acting on that, the superimposed solution, the linear superposition of those 2 solutions can be one of the solution of the same problem when both the set of forces are acting on the body simultaneously. Then after that we had discussed about the Saint-Venant's principle, which states the effect of loading for 2 different force systems which are statically equivalent to each other are only confined near around the zone of loading, and for the points which are far away from the point of loading there would be no difference between these 2 cases. So, this is known as the Saint-Venant's principle. Then coming to the next one, uniqueness theorem, this states that for a continuum, when it is subjected to given boundary conditions and given loading, external forces, body forces and surface tractions, for such cases the stress, strain and displacement fields can only have one set of unique solution. This is known as uniqueness theorem of elasticity. And then finally, Clapeyron's theorem, which states that the total work done by all the forces acting on a continuum divided by 2 is equals to the total strain energy stored within the continuum during this deformation. Now, we are going to discuss about 2 other theorems of elasticity in today's lecture. The first one is Beatty-Rayleigh reciprocity theorem, and the second one is principle of virtual work, sometimes that is also called the principle of minimum potential. So, first starting with the reciprocity theorem, Beatty-Rayleigh reciprocity theorem. So, here we are considering a continuum which is subjected to 2 different force systems. So, one particular force system consists of a set of surface traction and body force. So, as we are considering 2 set of forces or force systems which are acting on the same continuum, and under both of these 2 force systems the body is in equilibrium. So, for this continuum, whenever it is being acted upon by the first force system, there would be some kind of displacement fields resulted for this continuum, which we are denoting as U1. So, T1 and B1, this is the first system of force, surface traction and body force for first force system, which results a displacement U1 in the continuum. Then the same continuum, the same elastic body is subjected to second force system, where T2 is the surface traction and B2 is the body force corresponding to the resulting displacement U2 for the second case. Now, this reciprocity theorem states that for a same continuum, work done by the system of first forces acting through displacement of second system, that is U2, is equals to the work done of the second force system of forces acting through the displacement of U1 corresponding to the first system of forces. So, here the same continuum is considered, and 2 equilibrium states of the same continuum or same body is shown in this figure, but the forces acting on these 2 are different. So, for the first figure, the surface traction acting on the surface is equals to T1, and body force acting per unit volume is equals to B1, whereas for the second case the surface traction acting is T2 on the boundary and body force per unit volume is B2 within the body. Let us say U1 is the displacement for the continuum in the first case, whereas U2 is the displacement of the continuum in the second case. Now, as per the statement of this reciprocity theorem, the work done by the first system of forces T1 and B1 when it is acting upon second system displacement U2, that would be equals to the work done by the second system of force T2 B2 when it is acting with U1, the first displacement of the first force system. So, basically we are taking the opposite displacement and taking the force system from another one. So, we are not taking the corresponding displacement of individual force system, we are taking the opposite displacement and then finding the work done. If you do so for both the systems, then those two work done quantities should be same as per this theorem. So, if you are mathematically expressing this particular statement, it would be like this. So, left hand side terms are the work done by the first force system when they are acting upon by second displacement U2. So, the first term is a surface integral T1 dot U2. So, work done by all the surface tractions for the first case multiplied with the displacement of the second case integrated over total surface boundary plus volume integral of B1 dot U2. So, this is the work done by the body forces of first force system multiplied with displacement corresponding to second force system. So, these total work done of left hand side should be same as the work done by the second force system acted upon for first system's displacement U1. So, first term on the right hand side is T2 dot U1 integrated over the boundary gamma. This is surface traction work done for second surface traction force multiplied with first displacement, and the last term on right hand side is B2 dot U1 integrated over volume. This is the body force work done, that is work done by the second body force multiplied with the first corresponding displacement integrated over total volume. So, this is the statement or expression for the reciprocity theorem. Now, we will try to prove it. So, this was the statement written. Now, for the proof, we are first considering the left hand side. The work done by first force system T1 B1 when it is acting through the displacement U2, that work done I am naming as 1 2. So, first subscript of W, W12 is work done for the first force system when it is acting through displacement 2 U2. So, first subscript refers to the force, second subscript refers to the displacement in this W term. Now, W12 is surface integral T1 dot U2 plus volume integral B1 dot U2. So, first term is the work done by surface traction T1, second term is work done by body force B1, both due to displacement U2 corresponding to second force system. Now, writing T as sigma n or sigma transpose n using the relation between the surface traction and the Cauchy stress components, we can write T1 as sigma ij nj times ui integrated over d gamma is the total first term, and second term becomes integral over dv bi ui. Now, using the divergence theorem, this surface integral is changed to a volume integral and it becomes volume integral of sigma ij ui2, sigma ij1 uij2 entire thing comma j means del del xj of this quantity volume integral plus volume integral bi1 ui2. Now, this comma j term can be expanded, we can take the derivative once for sigma ij one term and then another ones for ui two term. So, first term is obtained by taking the time the xj derivative for sigma ij 1. So, it becomes sigma ij comma j 1 ui 2 volume integral plus second term is taking the derivative over ui 2. So, second term would be volume integral of sigma ij 1 uij 2 dv and plus the last term bi 1 ui 2 integral dv remain as it is. Now, using the equilibrium equation for the first state which is sigma ij comma j 1 plus b I 1. Using this, the combination of these two terms, this term and this term, these would result 0. So, that is from the equilibrium of the continuum when it is subjected to first system of force. Thus, W12 will be left out with only one non-zero term, that is integral of sigma ij1 ui comma j2 over the total volume of the continuum. Now, using the relation epsilon ij is equals to ui comma j. So, this we had derived and discussed multiple times in past few lectures, where epsilon ij can be written as ui comma j for the small displacement linear elasticity problem, and also assuming that strain tensor to be symmetric, epsilon ij to be symmetric, this condition can be shown or proved, which we had discussed. So, substituting that here, W12 becomes volume integral of sigma ij1 epsilon ij2 dv. Now, coming to the right hand side of the reciprocity theorem. So, left hand side of the reciprocity theorem is W12, which we had expressed in this form, volume integral of sigma ij1 epsilon ij2 dv. Now, coming to the right hand side, in a similar fashion, we define this as W21, that is work done by the second set of forces acting through the displacement u1 corresponding to the first force system, that is equals to surface area integral of T2 dot u1 d gamma integral plus volume integral of B2 dot u1 integrated over dv. And following a similar approach as discussed for the left hand side, this can be shown to be volume integral of sigma ij2 epsilon ij1. Now, our objective is to show that W12 and W21, that is this expression and this expression are same. If you are able to show that, then this particular Betti-Rayleigh reciprocity theorem would be proved. Now, let us start with the constitutive equation for proving this. So, if you are considering this first integrand term within the W12 expression, which is sigma ij1 epsilon ij2, we know that for linear elastic solid materials, the constitutive relation is equals to sigma ij equals to C I j k L epsilon k L, where C I j k L are the components of the fourth order elastic stiffness tensor. And note that this C is material property. So, it is independent to first force system or second force system. Material properties are not dependent on the forcing or boundary conditions of the system. So, this is always same. So, sigma ij1 is written here as C I j k L epsilon k L1 and epsilon ij2 is also existing. Now, we also know that this C matrix or elastic stiffness matrix is a symmetric one, which is showing two types of symmetry. One is called major symmetry of C I j k L, another one is minor symmetry of C I j k L. Now, here we are going to use the major symmetry property of C I j k L, which states C I j k L equals to C k L I j. The first two and last two set of indices can be flipped together, and using that, this C I j k L is written as C k L I j. Now, combining this C k L I j term with epsilon I j 2 term, we can write these two together as C k l I j epsilon I j 2, and this is nothing but sigma I j 2. So, sigma k l 2. So, if you recall, sigma I j is equals to C I j k l times epsilon k l. So, first two subscripts of C are same as the two subscripts of sigma, whereas last two subscripts of C are same as two subscripts of epsilon. Now, from here the last two subscripts are I j for C, they are same as the subscripts of epsilon. The first two subscripts of C k l should thus there be present in the subscripts of sigma. So, C k l I j epsilon I j 2 would be C k l 2 times epsilon k l 1, which was already there. So, thus we have shown that the sigma I j 1 epsilon I j 2 is equals to sigma k l 2 epsilon k l 1. Now, on the right hand side, both k and l are two dummy indices. Their names can always be changed to I j. We are substituting k with I and l with j on the right hand side, and with that sigma I j 1 epsilon I j 2 would be equals to sigma I j 2 times epsilon I j 1. So, now with this we have shown that the integrand present within the expression of W 1 2 and W 2 1 are same. So, if these two quantities are same, both of them integrated over the total volume would also be same, and thus W 1 2 is equals to W 2 1, and with that we are able to prove the Betti-Rayleigh reciprocity theorem. Now, moving to the next theorem of principle of virtual work. Here we are considering a continuum which is subjected to body force B per unit volume within it, and surface traction T is acting over some portion of the boundary which is gamma T, and for the remaining portion of the boundary we are having some displacement boundary condition prescribed over gamma u. So, you can see for this region of the boundary the displacement is fixed to be 0, and thus we call this part to be having the displacement boundary condition, whereas for the remaining part in this region the surface traction T is prescribed, where we can say the traction or stress boundary condition is existing. So, that is gamma T. Now, principle of virtual work first involves the definition of virtual displacement. So, the virtual displacement is defined to be a very small fictitious displacement at any material point, which occurs without any change of the forces acting at that point and without violating the boundary conditions of the continuum. So, at any point within the body, along with the actual displacement, we can add some small fictitious displacement. That displacement would be known as virtual displacement, but while applying that displacement we need to take care of 2 points. The first is the forces acting at that point are not going to get changed, and second point is while applying this virtual displacement we are not disturbing or violating any of the boundary conditions of the body. So, if such virtual displacements are possible to exist which are not violating the boundary conditions of the body, those are called admissible virtual displacement. Those are not violating any of the boundary condition and thus termed as admissible virtual displacement. Now, virtual work is defined to be the work done by the forces multiplied with the corresponding virtual displacement. So, at a point if you are assuming some virtual displacement, that multiplied with the force acting at that point would be equals to virtual work done due to that particular virtual displacement. If you are considering multiple virtual displacements at multiple points on the body, then the total work done, total virtual work done would be summation of virtual work done for each of the virtual displacement multiplied with the respective forces acting at those respective points. Now coming to the principle of virtual work, which states that the total virtual work done due to all admissible virtual displacements of a continuum in equilibrium is 0. So, you can apply n number of virtual displacement at different points within a body which are all admissible, means not violating any of the boundary conditions. Then if you calculate the total virtual work done of the body and that is coming out to be 0, then only the body is in equilibrium. So, if body is in equilibrium, we must have the total virtual work to be 0, which is resulted by all possible admissible virtual displacements which are not violating the boundary conditions. So, let us say delta ui. So, this delta operator is used for defining or expressing virtual displacement and virtual work done. So, delta ui is the virtual displacement vector at any point which is having 3 components, delta u1, delta u2 and delta u3. Now, due to this virtual displacement, some amount of virtual strain will be generated. Actual displacement was resulting actual strain. Now, with that, if you are adding this admissible virtual displacement, that would be resulting some amount of additional virtual strain. So, virtual strain due to virtual displacement delta ui can be written as delta epsilon I j, which is equals to half of delta ui comma j plus delta uj comma I. Now, note that delta ui is equals to 0 along the displacement boundary or gamma u, as the virtual displacement must be admissible. They cannot violate the kinematic displacement boundary condition. So, for this region gamma u, where displacement is already specified to be 0, at those set of points we cannot add any virtual displacement, that will cause the violation of the boundary condition. So, delta ui must be 0 over the surface over the boundary where displacement boundary conditions are prescribed. Now, moving forward to the proof of this principle, the virtual work done by all the forces, that is body force and surface tractions, can be combinedly written as delta w is equals to T dot delta u surface integral over d gamma plus B dot delta u surface volume integral over dV. So, first term is work done by the surface traction due to corresponding virtual displacements, and second term is work done by the body forces due to corresponding virtual displacements. So, writing this in the initial form, it would be surface integral of T I delta u I plus volume integral of B I delta u I. Now, using the relation between surface traction with the Cauchy stress components, T I is rewritten as sigma I j n j, and thus virtual work done delta w becomes the surface integral sigma I j n j delta u I plus volume integral of B I delta u I. Now, using the divergence theorem, by converting this first surface integral into volume integral, we are using the divergence theorem to do it, and we are getting volume integral of sigma I j delta I entire thing comma j derivative with respect to x j volume integral plus B I delta u I volume integral. Now, the first term can be divided by using the chain rule of differentiation. So, first we are taking differentiation of sigma I j, and in the next term we are taking differentiation of u I. So, thus on the right hand side we got 3 terms. Now, combining the first term and the third term, the sigma I j comma j term and B I term, these two, if we are summing up, that should be equals to 0 from the equilibrium equation. So, as the principle of virtual work states, when the body is in equilibrium, total virtual work done is 0. So, we are using that part of the statement, the body is assumed to be in equilibrium. Thus, this quantity sigma ij comma j plus bi must be 0. So, first and third term in combination would go to 0. Delta w is integral sigma ij delta ui comma j dv, volume integral. Now, we already know and proved this multiple times that epsilon ij is equals to ui comma j, and similar relation must be valid between the virtual displacement and virtual strains. Thus, delta ij is equals to delta ui comma j. So, under the assumption of existence of strain energy density function, that is capital U, strain energy density defined per unit volume, we can write sigma ij equals to del U del epsilon ij, and with the help of this the virtual work expression delta W can be rewritten as volume integral of sigma ij times delta epsilon ij dv, and replacing sigma ij as del U del epsilon ij, the total delta W would be volume integral of del U del epsilon ij delta epsilon ij. Now, we can combine these two terms with a single term of delta U. So, del epsilon U del epsilon ij delta epsilon ij can be written as delta U, where delta U is the variation of strain energy density function of the body. Now, using the definition of the virtual work delta W, which is total virtual work done by the surface traction T and body force B, replacing that on the left hand side, we can rewrite this expression as the volume integral of delta U minus surface integral of Ti delta Ui minus volume integral of Bi delta Ui equals to 0, where the first term refers to the change or variation in the total potential, total strain energy of the system, whereas next two terms in total gives us the overall virtual work done. So, this equation can be written as delta ut minus delta W, where ut is the total strain energy stored defined as integral of strain energy density over the total volume of the material. So, defining ut minus W as the total potential of the system denoted as pi, we must have delta pi to be 0 at equilibrium. So, this is the statement coming from principle of virtual work. So, delta pi equals to 0 at when the body is at equilibrium, where pi is defined as the total potential energy of the system equals to strain energy minus external work done. So, when the body is in equilibrium, variation of the total potential is 0, means the total potential is reaching a minima. The first variation of total potential must be 0 when the continuum is in equilibrium, and thus this principle is also known as principle of minimum potential. Potential energy should be minimum for a system when it is at equilibrium. Now, using this principle of virtual work, we can derive the equation of equilibrium along with the boundary condition. This is called the variational approach of solving any solid mechanics problem. So, starting with the statement of virtual work, which is volume integral sigma ij delta epsilon ij minus surface integral Ti delta Ui minus volume integral Bi delta Ui equals to 0. Using delta epsilon ij as delta Ui comma j, we are rewriting the first term, then we are writing this first term sigma ij delta Ui comma j as summation of two terms. One is sigma ij delta j comma j for the entire term minus of sigma ij comma j delta Ui. So, if you combine these two terms, you would get back this. So, first integral is distributed into two terms, third and fourth terms remain as it is. Now, we are using the divergence theorem for the first term, and thus using divergence theorem it is rewritten as surface integral of sigma ij nj delta Ui integrated over d gamma, and second term and fourth term, these two are combined together and written as sigma I j comma j plus b I delta u I volume integral minus surface integral of T I delta u I d gamma. Now, once again the first and last, these two terms are surface integral terms, those two can once again be combined. So, there would be two terms, one is volume integral term, another is surface integral term. The volume integral term would be sigma I j comma j plus b I delta u I dv integral plus the surface integral T I minus sigma I j n j entire thing multiplied with delta u I d gamma. This is the expression we are getting by simplifying the principle of virtual work. Now, this quantity to be 0 when the body is in equilibrium under the action of different forces and subjected to two types of boundary conditions, displacement boundary condition gamma u and traction boundary condition gamma t. To satisfy this above equation for any arbitrary virtual displacement, because virtual displacements are small fictitious displacements which are arbitrary, it can be any value but small and admissible to the boundary condition. So, for any arbitrary delta u I, the first volume integral term can be 0 only if the coefficient of delta u I goes to 0, means we must have sigma I j comma j plus b I equals to 0 over the entire volume, over the entire domain. With that, the first integral can be ensured to be 0, and this is nothing but the equilibrium equation of the system. Now, along with that, we must also satisfy the second integral to be 0, and second integral is defined over the surface boundary, not over the entire domain. So, on the surface boundary, either you should have this term equals to 0 or you should have this term equals to 0 on the surface boundary. So, either T I j is equals to sigma I j n j, which is the given value of sigma I j n j should be equals to T I or surface traction, that is condition for the surface traction boundary, and along with that the second part delta u I, that is defined for the displacement boundary. So, either T I sigma I j n j is 0, that is on gamma t, or we must have delta u I to be 0 on gamma u. Delta u I 0 refers to the case of u I to be constant, or that constant we can choose to be 0. So, u I 0 is occurring on the displacement boundary gamma u. So, either we should have this or this, and with this only we can satisfy the second surface integral going to 0. So, the first one is called natural boundary condition or traction boundary condition, whereas second one, which is prescribed on displacement, is called essential or geometric boundary condition. For any continuum deformation problem, it is essential to have at least one essential boundary condition with which the supports are defined. A body without any essential boundary condition means a body without support. It is not possible to solve such problems. So, essential boundary conditions must be there within the continuum, and with this approach we are able to show both equilibrium equation as well as two types of boundary conditions can be obtained with the help of principle of virtual work. So, this is called the variational approach of getting the equation of motion and boundary conditions of any body or continuum. So, in this lecture we had discussed about the two theorems, one is Betti-Rayleigh reciprocity theorem, another is principle of virtual work, which is also known as principle of minimum potential. Thank you.